we are talking about Evencycle and even matroids. So the first thing I want to do is remind you of what we mean by a sign graph. So a sign graph is a pair G sigma. So G is a graph, and sigma is a subset of the edges of the graph called the signature. And we're going to say that a cycle is even. A cycle C is even if C intersected sigma is even. And here by a cycle, I mean a set of edges that induced an Eulerian subgraph. So I have an example here. This is my graph. The red edges are the edges in the signature. And if I look at those wiggly edges there, that forms a cycle. I got two red edges. So that's an even cycle. And similarly, this is going to be an even cycle as well. So once I have a sign graph, what I can do is I can construct a 0-1 matrix in the following way. So I start off with the vertex edge incident matrix of the graph. So that's the matrix which has edges for each of the columns. And I'm going to add one extra row, which is the characteristic vector of the signature. So that's a 0-1 matrix. And now what I can do is I can look at the binary matroid, which is represented by that 0-1 matrix. And you can easily check that the cycles of that binary matroid are exactly the even cycle of my sign graph. So we're going to call such a matroid an even cycle matroid, and I will just denote it by E cycle, and then here we have the sign graph there. Okay, so that's the definition of even cycle. I should tell you what, before I do that, here's an observation. If my signature is just the empty set, then every cycle is an even cycle. So in particular, it tells you that the cycle of the graph is just the even cycle. So it implies that graphic matroids are example of even cycle matroid. So you get this little Venn diagram with even cycle, with graphic matroids, even cycles, and binary matroid. And I've placed some examples here, and if you notice here, I have the direct sum of F7 and 7, which in particular tells you that not everything is closed on the direct sum. Even cycle matroids are not closed on the direct sums. All right, so now I want to tell you what are even cut matroids. So let me remind you what is a graph. So graph is going to be a pair. You have a graph, and you have a subset of the vertices. I want that subset to have even cardinality. And I'm going to call those vertices terminals. And now in a graph, I'm going to say that a cut is even if it has an even number of terminals on both sides. So orange are my terminals. And here I have an example of an even cut, the wiggly edges there. And now similarly as before, I can say that the set of all even cuts of a graph forms the cycles of a binary matroid, and we call that binary matroid an even cut matroid. And I will denote it by E cut of GT. Right? Now, what happens if all my terminals is just the empty set? Then every cut is an even cut. So that will tell you that co-graphic matroid is a class of even cut matroids. All right, so even cycle matroids and even cut matroids are very closely related to graphic matroids and co-graphic matroid. They just lift of those matroid there. So you could say, okay, let's just look at nice results we have about graphic matroids. How hard can it be to generalize those to even cycles and even cut matroids? And in particular, I want to look at three results about graphic and co-graphic matroids. One is witness two isomorphism theorem. And then you have the problem of recognizing matroids, recognizing graphic matroids. This is a result of Tutte. And then you have Tutte's excluded minor characterization of graphic and co-graphic matroids. So I'm going to try to look at each of those results there. So let's start with the isomorphism result. Right? So let me just remind you of what is witness isomorphism result. So it says that if two graphs over the same edge set have the same set of cycles, then those two graphs are equivalent. And what do we mean by equivalent? Well, we mean that we can rearrange the blocks or the components of the graph, or we can rearrange the graph along two separation in this particular way there. So this is a two-flip. So you could ask the same kind of question about sine graphs, right? I give you two sine graphs which have the same even cycle. What is the relationship between those two between those two sine graphs? Or I could ask, well, I give you two graphs which have the same even cut. What is the relationship between those two graphs? Now, it turns out that actually those two questions are the same. So we just need to answer one of them. Now, why are those two questions the same? Well, we proved the following result. So if you give me a pair of graphs and they're not equivalent, if they're equivalent, I already know everything I want to know about those two graphs, namely the equivalent. But if they're not equivalent, then I can find a pair of signature such that they have the same even cycle if and only if I can find a pair of terminals so that they have the same even cuts. So just to illustrate this is an example. The red edges are your signature, and you can check that the even cycles here are the same thing as the even cycles there. Or you can pick in orange the terminals, and you can check that the even cuts here are the same thing as the even cut. So I'll just really consider the problem about sine graphs. All right, so let's just look at some example. Well, here's a Peterson graph. Now, it looks like I got Peterson graph and Peterson graph, but I'm interested in label graph. So what I've done here is I've shuffled the labels in a pretty nasty way, and I still have the same set of even cycle. That's a little scary. But maybe scarier is that I can take case 6, and I can shuffle the labelings, and you still have the same set of even cycles. So that looks a little scary. That's why I have unhappy face there. All right, so I don't know how to answer the question completely, but there are two nice partial results which I want to mention quickly. So there's an old result which I call the graphic case, and then there's a result that essentially proves answers the question for higher connectivity. So what is a graphic case? Well, this is a really nice result dating back from 1982. She was a PhD student of Neil Robertson. That's how I knew about this result there. And it says, well, suppose I give you a graph and I give you a sine graph, and the cycles of the graph are the even cycle of the sine graph. Then it tells you the relationship between the graph and the sine graph. And the details don't really matter, but the point is that it's something very explicit, right? You get one graph by identifying two vertices of the other graph, or you just rearrange things along free separation, and then there's a third construction. Now, unfortunately, that result, which is very nice, hasn't appeared anywhere except the PhD thesis, so it was never published. And so over the summer with my summer student, we found a nice short proof of that, and it really is quite short, as opposed to the original proof. Okay, so this is a graphic case. Well, we proved it for the four connectivity case. The result is a little technical to state, so let me just give you the vanilla version. So the hypothesis that we have is that G1 and G2 are four connected. I really don't want to have that here. I only have it because we don't know how to prove things otherwise. And they have the same even cycles. Then it tells you that three things have to happen. So the first one is the fuzzy one. Essentially, it tells you that I can change either G1 or G2 just a little bit, and then I'm back to the graphic case. I can just apply Xi's result. The second case is, well, you have K6 and K6. G1 and G2 are both K6. So K6 was really a sporadic example. Or you have a construction which is fairly general, that includes that example with the Peterson graph. But that fairly general construction, we know exactly what's going on in there. In fact, this was part of a paper we had with Paul and Irene. So for the four connected case, we know everything we want to know. All right, so let's move on to polytime recognition algorithm. So what can we do about even cycle and even cut? So let's just state the problem clearly. I'm given a matrix A, where all the entries are 0 and 1, and that's a matrix that represents my binary matroid M. And so what I want to know is kind of check whether my matroid M is an even cycle matroid in time polynomial in a size of A, or I want to answers the same question about even cut, right? So it turns out that we can do both results. Actually, it turns out that there's a common core to both results, but I'm only going to talk about the second problem there. But the first problem is not really disjoint from the second problem there. All right, so let me start with a sort of a naive approach for solving those kind of problems. So let me just say that a graph is a representation of my even cut matroid if, well, the even cuts of that graph are the cycle of the matroid there. And I start off with my matroid M, and I delete one element, contract one element, until I get down to something which has constant size. Maybe I want to keep them free connected along the way, right? And then, well, this has constant size, so I can get all the representations. So all the graphs where the even cuts give me my matroid there, right? And then I go from mk to mk minus 1 by on-deleting or on-contracting. So I can try to, get the representation of mk minus 1 from the representation of mk. That's not difficult. And you keep on doing that until you get all the representation of M. Now, if there is a representation, then it's an even cut matroid. Otherwise, it's not, right? So that's a fine algorithm, except that it's not polynomial. And what happened is that we have too many representations. Well, you're going to have lots of representation because you can do 1 and 2 flips. But there's another bigger problem. We have lots of inequivalent representations. So let me just give you that construction here. So what I do, I start off with a bunch of different graphs. So those are different graphs there. They all have 4 terminals, 1, 2, 3, and 4. And what I do is that I get the graph G1, T1 by identifying all the 1 vertices together and then all the 2 vertices together. So you can think of it as I just stack up all those different squares on top of one another. And then for G2, T2, I do almost the same thing, except I can take some of those pieces there and I can flip them. And I can flip them top to bottom, I can flip them left to right, or I can flip them diagonally. And it preserves the even cuts when you do that. But the problem is that there are an exponential number of ways I can get G2, T2 when you go there. So that tells you that the matroid that you have, which is represented by this graph there, right, has an exponential number of inequivalent representation. Right? Now that matroid also has 4 terminals, right? And it turns out that this is really the issue. So let me just give a definition here. We say that an even cut matroid is pinch cographic if there's a representation as a graph where I have at most 4 terminals. Right? So the example I gave you before was an example of a pinch cographic matroid that has an exponential number of inequivalent representation. Now it turns out that pinch cographic matroids are really the problem, because you have this other result that says that if I have an even cut matroid that is not pinch cographic, then it only has a finite number of inequivalent representation, right? So you really have this sort of completely different behavior. You go from exponential to just finite as soon as you're outside that special class. All right? And how do we use this result? We use it to show that if you want to check if a matroid is an even cut matroid in polynomial time, then all you have to do is to have an algorithm that checks if a pinch cographic matroid, if a matroid is a pinch cographic matroid, right? So we can now move on to just pinch cographic matroid, right? So I want to recognize if a particular matroid is a pinch cographic matroid. In other words, it has a representation as a graph with at most 4 terminals. So what do? Well, we still have lots of representations. So the idea is that we're going to bump up the connectivity. So we're going to work with almost 4 connected matroids. So what do I mean by almost 4 connected? I mean that it's going to be 3 connected. And if I have a free separating set X, either X or its complement is going to have at most 5 elements. And why is this nice? Well, this is nice because as soon as you're working with almost 4 connected matroid, pinch cographic matroids only have quadratic number of representations. So you went from having exponentially many different representations to just quadratic. And you might be wondering what happened to this example, right? So we had this example which is obtained by stacking up all of those pieces there. Well, this is just a flower. In fact, it's just an anemone. And each of those pieces there is just one petal of the flower. So if you take the union of an arbitrary number of set of petals there, it's going to be a free separating set. I don't have any big free separating set, so I can't have too many of those pieces there. So that kills my exponential construction. All right. And so, well, how do we go about now recognizing pinch cographic matroid? Well, we're going to do it in 2 steps. So first, we're going to recognize almost 4 connected pinch cographic matroids. So we can just keep track of representation in that case, right? Because we don't have too many, so it's just quadratic. But we'll need some other ingredient, right? We want to have a sequence of matroid which are all going to be almost 4 connected, right? But there's actually something stronger than a chain theorem. There's a splitter theorem for that class, for that type of connectivity, which is what we're using. So that's how we do the almost 4 connected case. But I really want to have an algorithm for the 3 connected part. That's a part of the paper that's not written yet. And so what do? Well, we decompose along free separations, right, until we get 2 pieces which are almost 4 connected. Then we use the other algorithm there. And then we just glue things back on free separation. Now that part is a little complicated. Free separations can look a little complicated. For instance, the blue and the green part there from a free separation there. But things can look a lot messier. So that part is a little tedious. Everything else in the almost 4 connected case is very clean. I think all the ugliness is left in that part there. All right, and that's the part about recognizing matroid there. And well, finally, you have the problem. You have a nice result for graphic matroids, namely, you have a characterization in terms of excluded minors by Tutte. So what is known in that case? Well, here's the bad news. Apparently, there are lots of excluded minor, I've been told, and lots is this looks very scary. And I think you can actually look at even cut matroids, and things are similarly bad, or you can look at combinations of classes, and everything looks pretty bad in terms of the number of excluded minors. The only positive result I know is just this result here recently, which essentially says that if things are highly connected, then you can actually characterize the excluded minors. But I'm not going to describe what this result actually says. And I'm going to stop here.
All right, are there any questions?
Do you think there's a hope of bounding the size of an excluded minor, even if you can't list them all?
Yeah, actually, I'm hoping about something maybe a little stronger. So I would like to have a result that says either you know, just a few steps away from being graphic, or I can actually give you a specific list. Okay. But I don't know if that's true. I mean, one could do the computation and maybe check it.
Any other questions? How do these techniques translate to ternary signed graphic matroids, if at all?
I'm not sure. Right now, I don't see how I would. So for the isomorphism theorem, I think that it really is very specific. I think maybe for the recognition, maybe this would extend. I mean, the general framework is that you want to somehow have this graph-like objects to represent your matroid. If you have not too many of them, you can keep track of them. And if you have too many of them, then you want to identify that you're in a special class. And then you want to do that class first. Right? So I think maybe that general framework works for more than just Evencycle and Evencut.